Hi guys, welcome back. Chapter 15 today, starting a new chapter. Going to look at section 1. This chapter is going to talk a lot about the behavior of solids, liquids, and gases. Okay, so today we're just talking about those three states. And in the next section we're going to focus a lot more on just gases themselves. Okay, so let's talk solids first. All right, solids by definition have a definite shape and volume. Okay, the particles of matter are very tightly packed. It's the slowest moving particles of matter per state, and they just kind of huddle up. Okay, so I have a marker here. It's obviously a solid. It doesn't change its shape when I put it in a different container. Okay, when we talk about liquids and gases, you'll see that's not true. But it doesn't matter if this is standing upright or on its side or in a cup or whatever. It still has the same shape and it still takes up the same amount of space. Okay. Now we have two different types of solids. We have crystalline solids, which form crystals, and we have what's known as amorphous solids. Morphology, morphing has to do with shape, and the prefix a means without, and so really an amorphous solid is one without a regular shape. Okay. Now the crystalline solids, those are our pure substances. Those are things like sugar and salt, things that have a regular melting point. Amorphous solids aren't considered pure structures and they don't have a distinct melting point. Okay? All right, moving on to liquids. So kind of keeping in the same type of definition, a liquid has a definite volume. It takes up a specific amount of space. I've got water in here. But it doesn't have a specific shape. It doesn't have a definite shape. It takes on the shape of its container. So if I pour this water in here, you can see now that the water has a completely different shape than it did when it was in this container. Okay? So liquids take on the shape of the container they're in, but they still take up the same amount of space. So the volume does not change regardless of the shape of the container. Okay? When we talk about liquids, we talk about this thing known as viscosity. And the viscosity is kind of a description of how thick the liquid is. The resistance a liquid has to flowing, and you can see in the picture up here, this liquid right here is pouring. It's flowing much more slowly than this one. Okay, so basically, the thicker the liquid, you would say that that's more viscous. It has a higher viscosity. And the more viscous, or the higher the viscosity, the slower the flow. Okay, so think of honey versus water. Okay, honey would be much more viscous than water. And next slide, I'm going to finish my point here, but then I've got to show you this crazy experiment on viscosity in just a second. But first, just so you know, a fluid is any substance that flows, and that includes both liquids and gases. We can talk about the viscosity of gases, but much more frequently we refer to viscosity with liquids only. Okay? All right, so this crazy thing is called the pitch drop experiment. And pitch is like tar. It's what's used, or it was used to seal boats, to make them waterproof, and for like roofing materials, things like that. Okay? So what you've got here is you've got this incredibly viscous, this is like the most viscous liquid there is. And you can see that it's very slowly forming a drip, okay? Well, this experiment has been set up since the 1920s. And only 9 drips have fallen off of this. It takes years before another drip falls, okay? But because it is technically flowing and because it is technically changing, it is considered a liquid and not a solid. Unfortunately, there used to be a live YouTube feed for it, and people could watch and just wait for the next drop. Sounds like watching paint dry to me. But anyway, they changed the container and something happened with the feed, and I don't think the feed has been up for a couple of years now. But anyway, this was set up in Australia in a museum, and it's the most viscous liquid in the world. All right, moving on to gases. Gases are a little harder to talk about because you can't see them. They're all around us, but again, following that kind of definition dealing with volume and shape, gases have neither definite volume or shape. Okay, their volume and their shape depends on the container they're in. And that I'm sitting in the classroom right now. So the container for the gas around me is the classroom. The doors are closed. That's not to say that some gas can't get in and out, but the gas in this room is filling the room and it's taking on the shape of the room, okay? If I blow up a balloon, it's filled with gas, and the gas takes on the shape of the balloon, takes on the volume of that balloon. But inside of the container now, those gas particles are spreading out. They're filling the container, and they're actually hitting the outside of this container. That's why a balloon stays inflated, because the gas particles are actually hitting the outside of it. We're going to talk a lot more about that in section 2, okay? But by definition, a gas has no definite volume or shape. It depends on the container, okay? And again, they spread out to fill all of the available space. And all of that available space might actually be the atmosphere. If you go outside, the atmosphere is filled with gas, okay? That's kind of the definition of the atmosphere. And then kind of bringing the movement of these particles together, the particles of gases move much more quickly than the particles of a liquid, but the particles of a liquid are moving faster than a solid, okay? So the solid state of matter has the slowest moving particles, although they are still moving, and gases have the fastest moving particles, okay? Let's talk about something that doesn't quite fit in the box. Okay, so what about shaving cream? I've got some shaving cream, and I'm just going to spray it onto this card. There we go. A nice dollop of shaving cream. Okay, so it definitely looks like it has a definite shape and a definite volume. Okay, the volume's not changing. The shape is not changing. In fact, this shape is actually strong enough that I can put a penny on it and it's going to balance there, okay? So my question is this a solid, okay? Well, no, because the shape is kind of gradually changing. I can touch it and move it, and when I touch it, it actually feels very airy, okay? So is it a gas? But a gas this isn't in a container, so how does it have any shape, okay? When I keep rubbing it, it actually will eventually go away, okay? So what does that mean, okay? And it feels a little wet. Is it a liquid? Who knows, okay? So again, it has definite shape and volume when you first spray it. It disappears when you rub it. Is it wet? It feels a little wet, but now it's just almost completely gone off of my hand. Does it have structure? Well, yeah, I put a penny on it, okay? So is it a solid, a liquid, or a gas? It's none of those. You need to research what shaving cream is. It's something different. It's something more complicated. You need to research what state of matter shaving cream is, and you need to email me the answer, okay? Yes, this is another assignment, and yes, this is just to make sure you're watching the videos that are so amazing. So get to it, and I eagerly await your answer. Talk to you guys later.